Right now, deep inside your body, there are particles that have existed since before the Earth formed. Protons. They sit at the centre of every atom in every cell. Scientists spent a century calling them immortal. But the math behind our deepest theories says every proton has an expiration date. We will travel to a pitch-black tank buried half a mile underground, filled with the purest water on Earth, where scientists are hunting for the moment a proton finally dies. If they find it, everything changes. If you enjoy what we uncover, subscribe. We begin.
Pick any object near you right now. A phone, a shoe, your own hand. Every single piece of it is built from atoms. And at the center of every atom sits a proton. Tiny, dense, positively charged. Protons are the reason elements exist. The number of protons inside an atom's center determines what that atom is. 1 proton makes hydrogen, 6 make carbon, 26 make iron. Change the proton count, and you change the element entirely. Protons are the identity cards of matter. Here is what makes them remarkable. A proton in your hand right now is the same proton that formed billions of years ago, not long after the universe itself began. It has passed through stars, through explosions, through the formation of planets, and through generations of living creatures. And it has never once changed. It carries no record of where it has been. It shows no signs of age. It just keeps existing, doing its job, holding matter together. For most of scientific history, nobody questioned this. Why would they? Protons seemed perfectly stable. They showed no signs of breaking down. Chemistry worked because protons stayed put. The entire physical world depended on their permanence, and they delivered every single time. Your body alone contains roughly 10 billion protons. That number is so large it breaks most comparisons. Every breath you take, every step you walk, every thought your brain forms, all of it runs on the reliability of protons. They are the foundation, under the foundation. But a question started nagging at physicists. Why are protons so stable? What actually keeps them together? An isolated neutron, the proton's close neighbor inside the nucleus, falls apart in about 15 minutes when pulled away from the nucleus. It breaks down into smaller pieces almost immediately. So why does the proton just keep going? For a long time, the answer was simple. Protons are the lightest particles that carry a specific type of charge called baryon number. The rule in physics is that baryon number must be conserved. A proton has nowhere to decay to because there is nothing lighter with the same charge waiting to receive it. That rule locked the proton in place, permanently, or so everyone thought. The assumption of permanence ran so deep that physicists built entire models of the universe around it. The periodic table, atomic theory, nuclear physics, all of it rested on the idea that protons simply do not die. They were treated like a law of nature rather than a question worth testing. And then, in the 1970s, something changed. A new generation of physicists started pushing the boundaries of what forces could be unified into a single theory. They were not looking for proton decay. They were not even thinking about it. But when the math came back, it carried an answer nobody expected. The proton was not as safe as everyone believed. The equations hinted that given enough time, a proton could transform spontaneously, without any outside force triggering it. The stability that the entire physical world depended on might have a limit. A slow one, a staggeringly slow one, but a limit. And if that limit is real, then every atom in your body, every rock on Earth, every planet orbiting every star, is sitting on a clock that is quietly ticking down. The question is how long that clock has left, and what happens when it finally runs out. Pull a single neutron out of an atom's nucleus and start a timer. In roughly 15 minutes, it breaks apart. It splits into a proton, an electron, and a tiny ghost-like particle called an antineutrino. Then it is gone. 15 minutes is all it gets. A proton sitting next to that neutron inside the same nucleus has been there for billions of years. Same neighborhood, same basic conditions, completely different outcome. That gap is one of the strangest puzzles in all of physics, and the answer to it reveals something deep about why matter exists at all. The neutron decays because it is heavier than a proton, even by a tiny amount. In physics, heavier particles want to shed mass. They find a way to transform into something lighter, if the rules of charge and energy allow it. The neutron has that option. It converts into a proton, which is lighter, and releases the leftover mass as energy carried away by the electron and the antineutrino. The math works. The decay happens. The proton has no such option. It is already the lightest particle that carries its specific type of charge. There is no lighter version waiting on the other side of the transformation. Physics has a strict rule called conservation of baryon number, and that rule says a proton cannot simply vanish or break into something lighter. It has nowhere to go, so it stays. That is the official answer physicists have given for most of the last century. And, for everyday purposes, it holds up perfectly. It explains why matter is stable. It explains why stars can burn for billions of years without their atoms crumbling. It explains why you are solid. But conservation of baryon number is a rule that comes from observation, not from a deeper law. Physicists have never found a fundamental reason why baryon number has to be conserved. It works in every experiment ever run. But working in every experiment and being an unbreakable law of nature are two very different things. That distinction matters enormously. If conservation of baryon number is just a very reliable pattern rather than an absolute rule, then the door stays open. The proton might decay. It might take an almost unimaginable amount of time, but it might happen. Picture a coin balanced perfectly on its edge. Every time you check, it is still standing. You check 1,000 times, 1,000,000 times, always standing. You might start to assume it can stand forever, but perfectly balanced is still balanced, and balance can break. The neutron showed physicists that particles can and do transform when the conditions allow it. The proton just needed conditions that were far more extreme. The universe is old. The universe is vast. And if proton decay is real, the universe has more than enough time. This single idea, that a rule physicists had never questioned might have a crack in it, opened one of the most ambitious experimental searches in the history of science. A search so difficult, it requires watching trillions upon trillions of protons at once, buried underground in complete darkness, hoping to catch a single one break apart. The search started with a theory, a very strange and very beautiful theory that tried to do something physicists had dreamed about for decades: unite all the forces of nature into one. In 1974, two physicists named Sheldon Glashow and Howard Georgi sat down with a problem that had been bothering the entire field for years. Nature has four fundamental forces. Gravity pulls planets together. Electromagnetism holds electrons in orbit and powers every light bulb ever made. The weak nuclear force governs radioactive decay. The strong nuclear force holds protons and neutrons together inside the nucleus. These four forces look completely different. They operate at different strengths. They work at different ranges. They seem to have nothing in common. But physicists had a nagging suspicion. In the early universe, when temperatures were unimaginably high, these forces might have behaved as one. As the universe cooled, they might have split apart into the four separate forces we see today. Glashow and Georgi decided to build the math. They wanted to write a single equation that could describe all the forces together. A grand unified theory. The name alone tells you the scale of the ambition. The math was elegant. It connected particles and forces in ways that felt almost too clean to be a coincidence. But to make the equations balance, something had to give. The framework required that quarks, the smaller particles that protons are built from, could occasionally transform into lighter particles, and if quarks can transform, the proton they are sitting inside can break apart. The theory did not say protons would decay quickly. The predicted lifespan was staggering, far longer than the age of the universe. But it was a lifespan, a number, a limit. The immortal proton suddenly had a death sentence written in the math. This was a genuine shock to the physics community. Conservation of baryon number had been treated as sacred. Now here was a respected theoretical framework, saying that rule was approximate, not absolute. Given enough time, a proton would find a way to transform. The immediate question was obvious. Can we test this? Can we actually catch a proton dying? At first glance, the answer seemed hopeless. The predicted decay time was so long that waiting for a single proton to die would take longer than every star in the sky will burn combined. No experiment could last that long. No scientist could wait that long. But then physicists remembered something beautiful about quantum mechanics. Decay is random, statistical. A single proton might last the full predicted lifespan, or it might decay tomorrow. The odds are just extraordinarily low. And here is the key. If you watch enough protons at once, the statistics shift in your favor. Watch a large enough group, and the odds say at least one should decay within a human lifetime. So the question became not how to wait for one proton, but how to gather enough of them in one place and watch them all simultaneously. The answer to that question would lead to one of the most unusual scientific facilities ever built. Something enormous, something buried, something filled with the purest water on Earth. But before anyone could build it, they needed to know exactly what they were looking for. And that meant understanding how a proton actually dies. The phrase grand unified theory sounds like something from a science fiction film, but the idea behind it is straightforward. Physicists believe the universe runs on rules, and the best rules are the simplest ones. If nature has 4 separate forces, maybe those 4 are just different faces of one deeper force that fractured long ago. A grand unified theory is the attempt to find that original face. By the mid-1970s, physicists had already unified 2 of the 4 forces. Electromagnetism and the weak nuclear force had been shown to be the same thing, at high enough energies. Call them the electro-weak force. That unification won a Nobel Prize and gave physicists enormous confidence. If 2 forces could merge, why not the others? The strong nuclear force was next in line. It is the force that grips quarks together inside a proton, holding them so tightly that separating them requires more energy than it took to form them in the first place. Merging this force with the electro-weak force required a new kind of math, a new symmetry, a new set of rules. When physicists wrote those rules down, the equations behaved beautifully. They connected quarks to other particles called leptons in ways that had never been seen before. Quarks and electrons, which seemed completely unrelated, turned out to be cousins under this new framework. They could transform into each other under the right conditions. And that is where the proton's death sentence entered the picture. A proton is made of 3 quarks, 2 up quarks and 1 down quark, bound together by the strong force. If quarks can transform into leptons, then those 3 quarks have a path. A rare, almost impossibly rare path, but a path. 2 of the quarks could interact through a new type of carrier particle that the grand unified theory introduced. That interaction would flip the quarks into lighter particles, and in doing so, the proton itself would dissolve. The most likely outcome, according to the simplest version of this theory, is that the proton spits out a positron and a particle called a neutral pion. A positron is the antimatter twin of an electron. A pion is a lightweight particle made of a quark and an antiquark. Both of them then decay further into pure energy. The proton becomes radiation. The carrier particle that triggers this whole process would be incredibly massive, far heavier than anything a particle accelerator on Earth can currently produce. That is why proton decay is so rare. The triggering particle almost never appears, but almost never is different from never. What this framework really tells us is that matter itself is not permanent in an absolute sense. The stability we see around us is a product of extreme rarity, not an unbreakable rule. Every solid object is a collection of particles that are incredibly unlikely to fall apart, but not actually forbidden from doing so. The implications spread far beyond physics labs. If the grand unified theory is correct, then the atoms in every mountain, every ocean, and every human body carry a timer built into the laws of nature. The theory made a specific prediction about how long that timer would last, and that prediction turned out to be wrong. Very, very wrong. Numbers in science can feel abstract. 1 billion years, 1 trillion years. The brain just hears a really long time and moves on. But to understand why proton decay is so hard to test, you need to actually feel the scale of the numbers involved. Start with the universe. It is about 13.8 billion years old. That is a long time. Every star that has ever burned, every galaxy that has ever formed, every living thing that has ever existed, fits inside that number. 13.8 billion years. Now consider this. The original grand unified theory predicted that a proton lives for roughly 100,000 trillion years before it decays. Write that out as a number and you get a 1 followed by 29 zeros. The age of the universe, that enormous 13.8 billion year span, is so much smaller than this number that it barely registers. If the universe's entire age were 1 single second, the proton's predicted lifespan would be over 300 billion years. The universe is a blink compared to it. And here is where it gets stranger. That original prediction turned out to be too short. Experiments have ruled it out completely. The actual minimum lifespan of a proton, based on what detectors have observed, is now over 10,000 trillion years, a 1 followed by 34 zeros, 5 orders of magnitude longer than even the original prediction. To picture this, imagine time as a road stretching from New York to Los Angeles, about 2,800 miles. The age of the universe takes up a single grain of sand near New York. The minimum proton lifespan extends the road past Los Angeles, past the Pacific Ocean, around the Earth, and out past the Moon. This scale creates an obvious problem. You cannot wait for a proton to die. Your experiment would have to run longer than the current age of the universe, thousands of times over. No government would fund that. No scientist would live to see the result. So the entire strategy of the hunt had to flip. Instead of patience, use numbers. Instead of watching 1 proton for an eternity, watch an astronomically large group of protons at once. Quantum decay is probabilistic. Any given proton might happen to decay early, the same way any given radioactive atom might happen to decay before its average lifespan is reached. If you pack enough protons into a detector and watch them all simultaneously, the math says that at least 1 should decay during a reasonable stretch of time. How many protons do you need? A rough calculation says you need something in the neighborhood of 1 trillion of them, all in one place, all being watched at the same moment. 1 trillion protons, sitting together, being watched for any sign of death. That is an enormous number, and it sounds impossible to gather in a lab. But there is a substance that is cheap, easy to obtain, and absolutely packed with protons. Water. A single drop of water contains more protons than there are stars in the entire Milky Way galaxy. And scientists figured out that if you built a tank large enough and filled it with enough water, you might actually have a real shot at catching a proton die. They just needed to build a tank big enough to matter. Imagine you are handed a single radioactive atom and told to watch it until it decays. The atom has a known average lifespan of 1,000 years. You sit down, you watch, and you wait. The problem is that the lifespan is an average. That specific atom might decay in 10 minutes. It might hold on for 10,000 years, Radioactive decay is completely random at the individual level. The average only appears when you look at a huge population of atoms together. Watch one and you learn almost nothing about timing. Proton decay works the same way. The predicted average lifespan is enormous, but any individual proton plays by its own odds. A proton that is statistically expected to live for 10,000 trillion years might decay tomorrow. The probability is fantastically small, but small is different from zero. This is the idea that makes the whole experiment possible. Physicists call it statistical detection. You gather such an enormous crowd of protons that even the tiniest probability of decay becomes likely to produce at least one event per year of observation. The math works like this. Take a group of protons large enough that multiplying the group size by the decay probability gives you a number greater than 1. That is your target audience. Inside that group, at least one proton should statistically decay during a reasonable observation window. A drop of water holds roughly 2 billion trillion protons. That sounds enormous, but even with a lifetime of watching, it would not be nearly enough. The probability per proton per year is so small that you need a tank holding thousands of tons of water before the numbers start working in your favor. And even then, you are not guaranteed to see anything quickly. You might watch for a year and see nothing. Or you might get lucky in the first month. The randomness never fully disappears. It just becomes manageable at large enough scale. This approach, gathering a massive group and watching them all at once, is the same logic used for every rare event detector in physics. It is how scientists detected neutrinos for the first time. It is how they found evidence of the Higgs boson. Rarity becomes catchable when you give it enough chances to appear. For proton decay, the numbers required pushed the experiment to a scale that had never been attempted before. The group of protons needed to be so large that the detector holding them would become one of the biggest enclosed scientific instruments ever built. And where do you put something that massive? Underground. Because the surface of the Earth is a storm of noise. Cosmic rays, particles fired across the galaxy by distant supernovas, rain down on every square foot of the planet continuously. At the surface, those particles would create false signals constantly, drowning out any real decay event before it could be identified. Dig deep enough, and the rock above acts as a filter. Most cosmic rays cannot punch through 1,000 feet of solid mountain. Get deep enough, and the background noise drops to almost nothing. The detector finally has a chance to hear the silence of the protons. But building something massive and burying it under a mountain is only the beginning. The detector itself had to be designed with extraordinary precision because the signal it was hunting for would be almost too small to see. The team of physicists who designed the Super Kamiokande facility faced a paradox from the very start. To detect something impossibly rare, they needed to build something impossibly large. But the larger the detector, the more vulnerable it becomes to noise from the outside world. Cosmic rays are the enemy. These are high-energy particles, mostly protons and atomic nuclei, that travel across the galaxy at nearly the speed of light and slam into the Earth's atmosphere constantly. When they hit the atmosphere, they create showers of secondary particles that rain down to the surface. At ground level, cosmic rays pass through your body hundreds of times every second. You never feel them, but they are real, and a sensitive detector would pick them up constantly. If you built the proton decay detector at ground level, and one of those cosmic ray particles passed through your water tank, it could mimic the signal of a decaying proton. The detector would fire, the team would get excited, and then they would realize it was just another cosmic intruder. This would happen so often that real signals, if any existed, would be completely buried in the false ones. The solution was elegant in concept and brutal in execution. Go underground. Put enough rock between the detector and the sky that the cosmic rays simply cannot reach it. Most particles in the cosmic shower are absorbed or deflected by solid rock. The thicker the ceiling, the quieter the experiment becomes. The site chosen was the Kamioka mine in Japan, a working mine already carved deep into Mount Akamo. The team did not have to start from scratch with the tunneling. They used existing infrastructure and expanded it to create a cavern large enough to hold their detector. The deepest part of the installation sits about 3,000 feet below the surface of the mountain. At that depth, the rate of cosmic ray particles passing through drops to almost nothing compared to the surface. The rock does what no artificial shield could do at a reasonable cost. It turns the mountain itself into a detector wall. But the rock is not a perfect shield. Some particles still get through. Muons, the heavyweight cousins of the electron, are so penetrating they can travel through thousands of feet of stone without stopping. And the rock itself is naturally radioactive, constantly emitting low-level radiation that the detector picks up as background noise. This meant the detector could not simply sit in the cavern and start recording. It needed its own inner layer of protection. The water inside the tank would serve double duty, first as the material full of protons to watch, second as a passive shield, absorbing low-level radiation from the surrounding rock before it could reach the most sensitive parts of the detector. The design that emerged was one of the most carefully thought-out scientific instruments in history. Every layer had a purpose. The mountain, the water, the sensors, all arranged in a specific order to give the faintest possible signal its best possible chance of being seen. Now the team needed to actually build the tank, and the scale of what they were about to construct inside a mountain was something most engineers had never encountered before. Standing at the edge of the Super Kamiokande tank and looking down would feel like standing at the edge of a skyscraper's open roof. The tank is a cylinder. It stands about 136 feet tall, roughly the height of a 12-story building. Its diameter spans about 129 feet across. That is wider than a standard American football field from end zone to end zone. The entire structure was carved and built inside a mountain. Workers blasted out the rock cavity first, then constructed the steel tank inside it. Every piece of steel, every cable, every piece of equipment had to be hauled through mine tunnels and assembled underground by hand. The logistics alone were a years-long engineering challenge, but the size is the first thing that stops you. This is a structure tall enough that you could drop the Statue of Liberty inside, torch and all, and still have room above it. The Statue of Liberty, measured from base to torch tip, stands just over 300 feet. The tank does not quite hold the full statue on its own, but the image gives a sense of scale that pure numbers cannot. The walls of the tank are not smooth steel. They are covered in sensors. Thousands of them packed closely together in a grid that covers almost every square foot of the inner surface. Each sensor is a glass sphere about 20 inches in diameter. These are the eyes of the experiment. Their job is to catch light, specifically the faint blue flash that a decaying proton would produce. Outside the main tank, there is a second, thinner layer of water and a second set of sensors. This outer layer acts as a veto system. If a particle enters from outside and triggers the outer sensors before reaching the inner tank, the detector knows to ignore that signal. It came from outside. It cannot be a proton decay. The engineering required to keep this structure running is relentless. The water must be continuously purified. The sensors must be monitored for failures. The electronics that read out millions of sensor signals per second must be maintained and calibrated. Hundreds of people work to keep the facility operating. And all of this effort, all of this cost, all of this engineering exists for one reason: to detect a flash of blue light so faint it involves only a handful of photons, a flash that might come once a year, or once a decade, or never. The detector does not promise results. It only promises the best possible conditions to detect something that might happen. And to make those conditions work, the water inside the tank had to be something extraordinary. Water was the obvious choice, but not for the obvious reasons. It is cheap, it is available in massive quantities, and it is easy to work with, compared to most materials. Those are practical reasons. But the physics reasons are what really sealed it. Water is made of 2 hydrogen atoms and 1 oxygen atom per molecule. Hydrogen atoms each contain exactly 1 proton. A single water molecule, therefore, contains 10 protons total, 2 from the hydrogen atoms and 8 from the oxygen nucleus. That is a very high proton density for something you can buy and pump through a pipe. A single drop of water, the kind that forms on the end of a faucet before it falls, holds more protons than there are stars in the entire Milky Way galaxy. The Milky Way contains somewhere between 100 billion and 400 billion stars. A drop of water beats that count easily. This is not a poetic comparison. It is a straightforward statement about atomic density. When you scale that up to the size of the Super Kamiokande tank, 50,000 tons of water, you arrive at a number of protons so large that even using scientific notation barely makes it feel manageable. The tank holds more protons than most people can meaningfully picture, and all of them are being watched. Simultaneously, every second the detector is running. Water also has another property that makes it ideal. It is transparent. When a charged particle moves through water faster than light can travel through water, it produces a specific kind of light called Cherenkov radiation. This light forms in a cone shape and emits as a blue glow. For that light to reach the sensors on the walls, the water has to let it travel across the width of the tank without being absorbed or scattered. Only very clean water does that reliably, which creates the challenge. 50,000 tons of water, purified to a level that seems almost absurd. Regular water, even filtered tap water, contains dissolved minerals, microorganisms, and trace chemicals that would scatter light before it could reach the sensors. The water in the Super Kamiokande tank had to be stripped of virtually everything in it. The purification system at the facility runs continuously. It cycles the water through filters, ion exchangers, and other treatment systems around the clock to keep it at the required purity level. The result is water so chemically empty that it behaves differently from anything you would encounter in everyday life. And that emptiness has a strange side effect, one that makes the water inside the tank unlike any water anywhere else on Earth. Pour a glass of tap water and hold it up to the light. It looks clear, clean, normal. In reality, that water is full of things you cannot see. Dissolved calcium and magnesium from pipes, chlorine added at the treatment plant, trace amounts of iron, copper, and dozens of other minerals picked up along the way. Microorganisms too small to see without a microscope. That glass of water is a busy chemical soup. The water inside the Super Kamiokande tank is almost the exact opposite. Scientists call it ultra-pure water. It has been stripped of essentially everything except hydrogen and oxygen. No minerals. No dissolved gases beyond trace amounts. No bacteria. No organic material. Just water molecules as close to the pure chemical formula as it is physically possible to achieve. The difference between tap water and ultra-pure water is not just a matter of cleanliness. They behave like different substances in important ways. Regular water conducts electricity because of the dissolved ions floating through it. Ultra-pure water conducts electricity very poorly. The minerals are gone, the charge carriers are gone, and here is the property that makes it feel genuinely alien. Ultra-pure water is hungry. Water molecules, left without anything dissolved in them, are extremely reactive. They want to pull ions and minerals into solution from whatever they touch. In normal water, this process is already happening constantly. The water is just already saturated with enough material that the effect slows down. Ultra-pure water has nothing in it, so when it touches something, it pulls from it aggressively. If you submerged your hand in the water inside the Super Kamiokande tank and held it there, the water would begin stripping minerals and nutrients directly from your skin. It would not burn or sting the way an acid might, but over time it would draw material out of you, leaching away the things your skin normally holds onto. Researchers who have entered the tank have worn full protective gear for this reason. The purification needed to create and maintain this water inside a 50,000-ton tank is a continuous industrial process. Water flows through the purification system around the clock, cycling back through to remove anything that has dissolved into it from the tank walls or the sensors. The facility essentially fights entropy non-stop, keeping the water in a chemically empty state that nature constantly tries to reverse. Why does this level of purity matter? Because even the faintest trace of radioactive material dissolved in the water would produce false signals. A single radioactive atom decaying inside the tank could produce a flash of light that looks like the signal the scientists are hunting for. The water has to be so clean that the only light appearing inside it comes from the protons themselves. Or at least, that is the goal. And the signal those protons might produce, when and if one finally decays, is something very specific, something the detector was designed to catch with extraordinary precision. A blue flash, moving in a cone, carrying the fingerprint of a particle that should no longer exist. Every experiment needs to know exactly what it is looking for before it starts. A proton decay experiment is no different. But the challenge here is unusual. The predicted signal depends on how the proton actually decays, and physicists have competing ideas about which pathway the proton would take. The simplest and most tested prediction comes from the earliest grand unified theories. When a proton decays along this pathway, it transforms into two things, a positron and a neutral pion. The positron is the antimatter partner of an electron, carrying the same mass but the opposite charge. The pion is a short-lived particle made of a quark and an antiquark. Both of these products are unstable. The neutral pion breaks apart into two photons, which are particles of pure light, within less than a millionth of a billionth of a second. The positron quickly encounters an electron in the surrounding water, and the two annihilate each other, also producing light. The net result of one proton decaying is a brief burst of light and energy, carrying a specific total energy equal to the proton's original mass. The signal is distinctive. The total energy released equals the mass energy of one proton spread across a handful of particles moving outward in a specific pattern. The detector's sensors can measure the direction and energy of each particle. If the measured energies add up correctly and the geometry of the signal fits the expected pattern, that is a candidate event. This specificity is crucial. The detector sees enormous amounts of noise, natural radioactivity, cosmic ray muons that slipped through the rock, particles produced by neutrinos passing through the water. Each of these has a characteristic signature too. The proton decay signal has to be distinguishable from all of them. Scientists spent years building software models of what a genuine decay event should look like. They simulated thousands of fake events and trained their analysis tools to recognize the pattern. The goal was to reach a point where a real signal, if it appeared, would stand out with enough confidence to be called a discovery. There is also a second possible decay pathway that the simplest theories do not cover. A more complex version of the theory, one involving a concept called supersymmetry, predicts that a proton might instead decay into a kaon and a neutrino. The kaon is a different kind of lightweight particle. The neutrino is a ghost particle that barely interacts with anything. This second pathway would produce a much harder signal to catch. The neutrino flies straight through the water and the tank walls without triggering a single sensor. Only the kaon signature would remain. And a kaon alone leaves a much fainter, less distinctive trail. Two different signals, two different theories, both pointing toward the same fundamental conclusion. The proton eventually dies. The detector had to be sensitive enough to see either one, and to do that, it needed something extraordinary lining its walls. Light travels at a fixed speed in a vacuum. That speed, roughly 186,000 miles per second, is the absolute maximum in empty space. But inside a material like water or glass, light slows down. It has to interact with the atoms it passes through, and those interactions slow it down. In water, light travels at about 3/4 of its vacuum speed. This creates a loophole. In water, the speed limit for light is lower than it is in open space, and some particles can travel through water faster than light travels through water. They are not breaking any fundamental law, they are just moving faster than light can move in that specific material. The absolute cosmic speed limit, the speed of light in a vacuum, remains untouched. But when a charged particle outruns light in a medium, something strange happens. The particle disrupts the water molecules as it passes through, and those molecules release light as they recover. Normally, if a particle were moving slower than light in the water, that released light would spread out ahead of the particle and wash away in all directions. But when the particle is moving faster than the light itself, the light piles up behind the particle in a cone shape, like a sonic boom. A sonic boom is the wall of compressed sound that forms when a jet aircraft outruns its own sound waves. The sound cannot escape ahead of the jet. It gets pushed into a cone. Cherenkov radiation is the light version of that effect. A cone of light trails behind the fast-moving particle, angled outward from its path. And that light is blue. It is not blue by accident. The cone contains light across many frequencies, but the geometry of how it spreads and how the human eye and the sensors detect it puts the peak intensity in the blue part of the visible spectrum. The eerie blue glow you see in photographs of research reactors is Cherenkov radiation from fast electrons produced by the nuclear reaction passing through surrounding water. When a proton decays and produces a positron and a neutral pion, those products travel through the water at speeds faster than light can move through it. They each produce their own Cherenkov cone. The sensors on the walls of the Super Kamiokande tank detect the ring patterns of those cones hitting the walls. Each ring carries information about the particle that made it, its speed, its energy, its direction. The entire detection strategy is built around seeing these rings. The thousands of sensors that line the tank walls watch for the blue light of Cherenkov radiation, waiting to see the specific ring pattern that only a proton decay could produce. Every other known background event makes different rings, different patterns, different energies. The rings are the fingerprint. Find the right rings in the right pattern with the right energy, and you have found your decaying proton. But first you have to be able to see a fingerprint that might appear only once in years of watching. Cover a surface the size of a baseball stadium's outfield wall with glass spheres, each one about the size of a basketball, and you start to approach the density of sensors inside the Super Kamiokande tank. Over 11,000 individual light detectors line the interior walls of the cylinder. They cover the curved wall, the flat circular floor, and the ceiling above. Each sphere is a device called a photomultiplier tube. The name sounds complex, but the basic idea is simple. A single photon of light, the smallest possible unit of light energy, strikes a sensitive surface inside the sphere. That interaction knocks loose a single electron. The device then amplifies that single electron into a cascade of millions of electrons, producing an electrical signal large enough to measure. The original photon, which carried almost no energy, becomes a detectable pulse. The detector can find a single photon of light crossing 50,000 tons of water. That sensitivity level is genuinely extreme. For comparison, the human eye can detect somewhere around 5 to 10 photons at a time under ideal conditions. The Super Kamiokande sensors can work with even fewer, and they can precisely measure when the photon arrived, down to a small fraction of a second. Timing matters enormously in this experiment. A proton decay would release particles that travel outward from a central point. Those particles would hit different parts of the tank wall at slightly different moments, depending on how far each sensor is from the origin point. By recording exactly when each sensor fired and what energy it detected, the analysis software can reconstruct the three-dimensional shape of the event. It can calculate where in the tank the event happened, in what direction the particles moved, and how much energy each one carried. This reconstruction is the tool that separates signal from noise. Background events, cosmic muons, natural radioactivity, neutrino interactions, all leave their own patterns. Most of them produce tracks that originate from outside the fiducial volume, the inner region of the tank that the analysis focuses on. A real proton decay would originate from inside the water, appearing from nowhere with a specific energy signature. The outer ring of sensors, the veto layer surrounding the main tank, adds another layer of protection. Any event that simultaneously triggers the outer sensors is flagged immediately as an incoming particle from outside. It cannot be a proton dying from within. The software processes the firing patterns from all 11,000 sensors and makes decisions constantly every day, in real time. Most events are discarded quickly as known backgrounds. What remains after filtering is a much smaller set of candidates that require closer human review. For decades, every candidate that made it through the filter was eventually explained. Cosmic ray, natural decay, neutrino interaction. The tank speaks constantly. But the specific conversation the physicists are waiting for has never started. When physicists first wrote down the equations for the grand unified theory in the 1970s, the prediction was specific. A proton's average lifespan would be roughly 10,000 trillion years, or in shorthand, a 1 followed by 29 zeros. That number felt safe. It was enormous, nearly unimaginable. Surely nature would not allow scientists to confirm or deny something so extreme. They were wrong about that. The original Kamiokande experiment in Japan began running in 1982. It was smaller than what came later, holding about 3,000 tons of water and lined with a few hundred sensors. Scientists filled it with water, buried it underground, and started watching. The theory predicted that with enough protons in the tank, at least a few decays should show up within the first year or two of running. The experiment waited. No signal appeared. The team analyzed their data carefully, searching for any event that matched the expected signature. Nothing passed the test. Each year of silence carried a scientific message. If proton decay were happening at the rate the theory predicted, the experiment should have detected it. The fact that it had not meant the actual decay rate was slower than predicted. The true lifespan had to be longer than the original estimate. By the time the first Kamiokande run had gathered enough data, the original prediction had already been ruled out. The minimum proton lifespan, based on the absence of any signal, had been pushed past the point where the simple grand unified theory could survive. The theory as originally written was eliminated. This was a significant result. The experiment had not failed. It had succeeded at something important. It had killed a major theoretical framework through direct observational evidence. Science at its most functional. But killing one version of the theory did not kill the concept of proton decay. Physicists went back to the drawing board. They adjusted their models. They found ways to write grand unified theories that predicted longer proton lifespans, ones that the experiment had not yet ruled out. The hunt continued. The decision came to build something vastly larger, a detector so massive that even the longer predicted lifespans would start to come within reach of detection. More water, more sensors, more protons under watch. This led to Super Kamiokande, built in 1996, with 50,000 tons of water and over 11,000 sensors. The new facility started watching, and now the silence was being heard by much more sensitive ears. The minimum confirmed lifespan of a proton climbed higher with every passing year of no signal. Each new dataset extended the lower bound. Each extension ruled out another class of theoretical models. The experiment was succeeding by hearing nothing, and every moment of quiet pushed physics into territory it had never mapped before. But somewhere in that silence was a deeper mystery, one that started to make some physicists wonder whether the grand unified theory approach was fundamentally on the right track at all. The Super Kamiokande detector has been running since 1996. That is nearly 3 decades of continuous operation. During that time, the sensors have recorded hundreds of millions of events. Cosmic muons punching through the rock and into the tank, neutrinos passing through the Earth and interacting with the water molecule, background radiation from trace elements in the tank walls. The detector is not quiet, it is extraordinarily busy. But through all of that activity, through all of those recorded signals, through every careful analysis of every candidate event, there has been zero, not one confirmed proton decay. The specific pattern, the specific energy, the specific combination of particles that would tell scientists a proton had finally broken apart has never appeared. This is called a null result. And in physics, a null result can be just as powerful as a positive one. The silence is not a failure. It is data. Here is what the silence means in concrete terms. If protons were decaying at the rate the original theories predicted, the Super Kamiokande tank should have seen thousands of decay events by now. It has seen none. That means the original predictions were wrong by a very wide margin. The silence forces the minimum lifetime of a proton upward, past any number the original theories ever imagined. Picture a fisherman who drops a net into the ocean every day for 30 years and never catches a specific kind of fish. The longer this goes on, the more certain he becomes that the fish is either extremely rare or lives far deeper than his net reaches. He has not proven the fish does not exist, but he has proven it is much rarer than anyone first thought. The Super Kamiokande silence does the same thing. It proves that proton decay, if it happens, occurs far less often than the simplest theories expected. The fish exists in the theory, but it is either too rare to catch yet, or it decays by a different pathway than the one the net was built for. Scientists built their analysis software to recognize the most common predicted decay modes, a proton becoming a positron and a pion. The signal was not there. Then they searched for secondary decay modes, rarer pathways predicted by more complex theories. Still nothing. The minimum confirmed proton lifetime now sits above 10,000 trillion years, a 1 followed by 34 zeros. Every additional year of silence adds another layer to that bound, pushing it higher and ruling out more theories. Some physicists started feeling a creeping unease. The silence stretched past the point where the simplest theories could explain it, into a range where even modified theories were struggling. The question was starting to shift from when will we detect proton decay to whether proton decay is even real. The answer to that depends heavily on which version of the underlying physics turns out to be correct. And one version of the theory predicts a decay pathway so difficult to catch that the silence might mean almost nothing at all. Every year that the Super Kamiokande detector runs without finding a proton decay, the minimum possible lifespan of a proton gets pushed higher. This is not a defeat. It is the experiment doing exactly what it was built to do. Measuring silence is a form of measurement. Here is how the bound gets raised. If protons decayed at a rate consistent with a given predicted lifespan, then statistically, a certain number of decays should have appeared in the data by now. If 0 have appeared, then that predicted lifespan is too short. The actual lifespan must be long enough that none of the protons in the tank have had time to decay yet, even over nearly 30 years of watching. Each additional year of data without a signal is another constraint, another theoretical model crossed off the list. The experiment is not sitting still, even when the water is. This kind of measurement is called a lower bound. Scientists cannot say exactly how long a proton lives. They can only say it lives at least this long, because any shorter lifespan would have produced a signal by now. The lower bound has been pushed up so far that it sits well above the lifespan that would have been predicted by the original grand unified theories. The practical effect of this climbing bound is that physicists working on theoretical models must keep pace. Every model that predicts a proton lifetime shorter than the current lower bound is eliminated. Only models that predict longer lifespans remain viable. And the longer the predicted lifespan, the harder it becomes to ever test the theory. There is a ceiling to this process. If the true proton lifespan is so long that even a detector the size of a small ocean could not catch a single decay event in a human lifetime, then the theory becomes practically untestable. It would be true or false, but science would have no way to find out. That boundary between testable and untestable is closing in on the proton decay question from one side. The detector can be scaled up. More water, more sensors, more protons under watch. All shift the lower bound higher and faster. This is why a new, much larger detector is being built. But even the largest planned detector has limits. What makes this period of the experiment feel particularly intense is the direction the silence is pointing. The original simple theories are gone. The remaining viable theories require either very long proton lifespans or different decay pathways than the ones being tested. Both of these possibilities make the experiment harder. And one of those alternative pathways involves a particle that is almost impossible to detect. A particle that could be carrying the secret of proton decay through the tank walls right now, invisible to every sensor in the facility, without leaving a single trace. If that pathway is the right one, the hunt becomes an entirely different kind of challenge. Silence in a physics experiment rarely means nothing happened. It usually means the universe gave an answer, and the answer was harder to hear than expected. The silence from the Super Kamiokande tank has eliminated entire categories of grand unified theories. The simplest versions, the ones written in the 1970s and celebrated for their elegance, are gone. The detector proved they were wrong by simply running long enough without confirming their predictions. What remains is a smaller, more complex set of theories. These surviving models share one feature. They predict proton lifespans long enough to escape detection so far. Some of them predict lifespans that the current detector may never be able to reach. They stay alive precisely because the experiment has not yet accumulated enough data to rule them out. This situation reveals something important about how science actually works at its frontiers. A theory does not survive because it has been proven right. At this stage in the proton decay hunt, a theory survives because it has not yet been proven wrong. The silence is a filter. Every year it runs, the filter becomes finer. The theories that remain are the ones flexible enough to accommodate the growing lower bound. Some physicists read the silence as a sign that the entire grand unified theory framework needs rethinking. The original motivation for the framework was elegant and compelling, but if none of the predicted signals have appeared after decades of searching, maybe the math, despite its beauty, is pointing in the wrong direction. Science has no loyalty to beautiful theories. It follows evidence. Others argue the opposite. The silence is exactly what you would expect if the true proton lifespan is very long. A longer lifespan means fewer decays per year, which means a bigger detector is needed. The absence of a signal is not a failure of the theory. It is a challenge to the experimentalists to build something larger. Both positions are scientifically honest. Both have supporters among serious physicists, and both lead to the same practical conclusion. The experiment must grow. The Super Kamiokande facility has not run its course. It continues to collect data. Each new year pushes the lower bound slightly higher, slightly tighter. Each new analysis refines what kinds of signals the team is looking at. The hunt continues. But a parallel question has been growing alongside the silence. What if the proton decays along a pathway that produces a particle the current detector cannot see at all? What if the silence is not because protons live longer than expected, but because they are dying in a way that leaves no visible fingerprint in the water? That possibility involves supersymmetry, a theoretical framework that expands the particle zoo in ways that change everything about how a proton might break apart. And if supersymmetry is right, the decay happening right now inside the tank might be completely invisible to every sensor currently installed. The simplest version of proton decay produces a positron and a pion. Both of those particles move through water at high speed, produce Cherenkov light, and leave rings on the tank walls that sensors can read clearly. The signal is detectable. That is why the Super Kamiokande detector was designed around it. But a competing theoretical framework, called supersymmetry, predicts a completely different outcome. Under supersymmetry, every known particle has a heavier partner particle that has never been directly observed. The math of supersymmetry changes the internal dynamics of proton decay. The quarks inside the proton follow a different transformation path, and the result is a completely different set of decay products. Instead of a positron and a pion, supersymmetric proton decay produces a kaon and a neutrino. The kaon is a heavier cousin of the pion. It carries a type of particle content that the pion does not, and it leaves a different kind of signature in the water, detectable but harder to isolate from background noise than the cleaner positron-pion signal. The neutrino is the real problem. A neutrino is a particle with almost no mass and no electric charge. It barely interacts with ordinary matter at all. Every second, trillions of neutrinos from the Sun pass straight through your entire body without touching a single atom. They pass through the Earth as though the planet were not there. They pass through the Super Kamiokande tank, through 50,000 tons of water, through 11,000 sensors, and out the other side without triggering a single detector. If the supersymmetric decay pathway is correct, then every proton decay happening inside the tank produces a neutrino that immediately escapes undetected. The neutrino carries roughly half the energy of the original proton straight through the walls and into the surrounding rock. Invisible and unrecoverable, the only trace left behind is the kaon. This changes the energy calculation completely. The sensor array is programmed to look for events where the total energy matches the mass of a proton. If half that energy vanishes with the neutrino, the remaining signal is weaker and harder to distinguish from background events that produce similarly low energy signatures. The Super Kamiokande team has searched for this kaon neutrino signal too. They updated their analysis software and ran dedicated searches. The result was the same: silence. But the silence on this channel is less informative than the silence on the positron-pion channel, because the signal is harder to find even in principle. The lower bound established by the kaon neutrino silence is less restrictive. There is more room for the theory to hide. What this means is that supersymmetric proton decay could be happening inside the tank right now, at a rate that should be detectable by a more advanced instrument, and the current setup might simply be missing it. Every day, protons could be transforming into kaons and neutrinos, with the kaons leaving faint signals that blend into background noise, and the neutrinos vanishing entirely. The hunt for this second pathway requires a different approach: larger detector volume, better sensor coverage, a more sensitive ear, listening in the dark. That more sensitive ear is already being built. To understand why the neutrino complicates the proton decay search so severely, it helps to understand what a neutrino actually is and why physics has such a hard time pinning it down. When the Sun fuses hydrogen into helium in its core, it releases neutrinos as a byproduct of that reaction. The Sun produces roughly 200 trillion neutrinos every second. That number sounds impossible, but it is a straightforward result of nuclear fusion physics. Every square inch of your skin facing the Sun is being hit by roughly 60 billion solar neutrinos every second, right now, in this moment. You feel nothing. They pass through your body without interacting with a single atom. Neutrinos carry no electric charge, which means the electromagnetic force cannot grab them. They have almost no mass, which means gravity barely touches them. The only force that can interact with them is the weak nuclear force, and that force operates at extremely short ranges. The odds of a neutrino triggering a weak force interaction as it passes through a detector are extraordinarily small. To detect a neutrino, you essentially have to get lucky. You need an enormous amount of target material, and you need to watch it long enough that occasionally one neutrino in a vast stream of them happens to interact The Super Kamiokande detector was actually built partly for neutrino physics alongside the proton decay search. Its 50,000 tons of water give neutrinos enough material to interact with that the facility can detect hundreds of solar and atmospheric neutrinos each year. But detecting a neutrino as a product of proton decay is a completely different problem. You cannot see the neutrino directly. You can only infer it was produced by noticing that some energy is missing from the event. If a proton decays and the remaining particles account for only half the expected energy, the missing half presumably flew away as a neutrino. This inference is fragile. Many background events also look like partial energy deposits. A neutrino from the atmosphere interacting with a water molecule can produce a kaon and leave the rest of the interaction energy, distributed in ways that mimic a proton decay. Separating the real proton decay signal from these background interactions requires extreme precision. The Super Kamiokande upgrade, completed in 2020, addressed this problem. Scientists added a rare earth material called gadolinium to the water. Gadolinium has an exceptional ability to capture neutrons and release a distinctive burst of gamma rays when it does so. This allows the detector to tag neutron-producing background events more accurately and separate them from the events it cares about. Even with that upgrade, the neutrino remains mostly invisible. It leaves the tank taking its secrets with it. The kaon it left behind is the only clue. And a single clue in a tank full of noise is a very thin thread to pull on. The Super Kamiokande experiment pushed the boundaries of what its generation of technology could do. Now a new project is pushing further. Hyper Kamiokande, currently under construction in Japan near the original site, represents the next leap in the search for proton decay. The scale difference between the two detectors is striking. Super Kamiokande holds 50,000 tons of water. Hyper Kamiokande will hold roughly 260,000 tons. That is more than 5 times the water volume. 5 times more protons under watch. 5 times more chances per year to catch a decay event. The new tank stands taller and wider than its predecessor. The design is similar in concept, a deep cylindrical water tank lined with photomultiplier sensors, but everything has been scaled up and refined. The new sensors are more efficient than the ones installed in the original facility. They capture a higher fraction of the Cherenkov light that crosses the water, which improves the energy resolution of each event and makes it easier to separate signal from noise. The location is also important. Hyper Kamiokande is being built under a different mountain with even more rock overhead, providing better shielding from cosmic ray muons that sneak through even the considerable coverage at the original Kamioka site. Fewer cosmic muons mean fewer false signals, which means the team can be more confident about any candidate event that does appear. The facility is designed to serve multiple purposes simultaneously. It will function as a proton decay detector, pushing the lower bound on proton lifetime several times higher than the current limit. It will also serve as a world-class neutrino observatory, tracking neutrinos from the Sun, from the atmosphere, and from the Japanese particle accelerator facility that fires a neutrino beam directly through the ground toward the detector. For the proton decay search specifically, the larger volume of Hyper Kamiokande changes the math significantly. If the true proton lifetime falls within certain ranges predicted by surviving theoretical models, the new detector should be able to accumulate enough statistical evidence within 10 to 20 years of operation to either confirm decay or rule out another large class of theories. The gadolinium upgrade from Super Kamiokande is being incorporated from the start in the new design, making it sensitive to the kaon neutrino decay channel from day one, rather than requiring a retrofit. Hyper Kamiokande represents a generational commitment. The physicists who designed it know they may be building something whose most important result, if one comes, might arrive after their careers are over. They are building it anyway, and if the proton continues to stay silent, even inside this larger ear, the implications for physics would be profound. The silence would be speaking louder than ever. Every measurement, ever made of a proton, in every lab, in every country, across every decade of modern physics, has produced the same result. Protons appear completely stable. No decay, no change, total consistency. But a handful of theoretical physicists have started asking a quieter question. What if that consistency is local? What if the stability of a proton is not a fixed property of nature, but something that can shift under extreme conditions? Standard physics treats fundamental constants as universal. The speed of light is the same everywhere. The charge of an electron is the same everywhere. Proton stability, under the most conventional models, should also be the same everywhere. But some theoretical frameworks allow for something stranger. The vacuum of space, the seemingly empty backdrop of the universe, has physical properties. It has an energy density. It was in a different state in the early universe than it is today. If the vacuum can change states, and physicists know from the early universe that it can, then the rules governing particle behavior might shift along with it. Under certain extreme conditions, very high temperatures, very high densities, or regions where space-time itself is severely distorted, the effective rules of particle physics might differ from what we measure here on Earth. In those environments, the barriers that prevent proton decay could weaken. This would mean that protons are genuinely stable under the conditions we live in, but unstable in places like the cores of collapsing stars, the regions near black hole event horizons, or the early moments after the Big Bang, when the universe was compressed into a space smaller than a single atom. If true, this creates a strange picture. Protons in your body are stable. Protons near the center of a neutron star might be decaying constantly. The experiment in Japan would never detect them, because those protons are in an environment entirely unlike the ultra-pure water of the tank. This idea remains deeply speculative. There is no experimental evidence supporting it. The math that generates this possibility comes from specific theoretical frameworks that have not been confirmed in any other way. But the possibility itself is scientifically legitimate. The history of physics is full of quantities that seemed universal until measurement showed they were not. The practical challenge is that these extreme environments are impossible to recreate in a laboratory. Testing whether proton stability changes near a black hole requires a detector near a black hole, which is not on any current roadmap. For now, every test of proton stability is a test under normal conditions, and under normal conditions, the proton has shown no sign of weakness, which raises the strange possibility that the proton is perfectly stable exactly where we can test it and transforming freely in all the places we cannot see. The numbers around proton decay are so large, they stop feeling real after a while. A 1 followed by 34 zeros, the age of the universe times a trillion. These figures describe something so slow it might as well be frozen. But there is one way to bring the scale back down to something personal. Your body contains roughly 7,000 trillion atoms. Each of those atoms has a nucleus, and in that nucleus sits at least one proton. Adding up the hydrogen atoms alone, your body carries somewhere around 10 billion protons, that is a 10 followed by 28 zeros. Now apply the fastest theoretical decay rate that has not yet been ruled out by experiments. Under that rate, if you spread your body's protons out over the predicted minimum lifespan, the math produces a striking result. Statistically, over the course of an average human lifetime, somewhere between 1 and a few of the protons in your body might decay. Might. If the true proton lifetime is near the lower end of what is still theoretically allowed, and if proton decay is real at all, then at some point in your life, a proton inside one of your atoms could transform into a positron and a pion, release a tiny burst of energy, and vanish. You would feel nothing. The energy released is minuscule compared to the chemical reactions happening in your cells every millisecond. The event would be completely imperceptible. The atom that lost its proton would become a different element, but a single atom changing identity inside a body of trillions has no biological consequence. The event would be silent, invisible, and completely undetectable without instruments far beyond anything that could be implanted in a living thing. But statistically, the possibility exists. This framing makes the abstract personal. The hunt happening inside a mountain in Japan is not just about physics equations. It is about whether the material you are built from carries a hidden timer, whether the atoms that make up your bones and your brain and your blood are slowly, imperceptibly counting down. If protons decay, then matter itself has an expiration date built into every particle. Your body is a temporary arrangement of particles that will one day dissolve, not just into smaller molecules or simpler chemistry, but all the way down into pure radiation. The solid becomes light, and your body is just a small example. The question scales upward to everything, every rock, every ocean, every dead star drifting cold through the galaxy. If protons decay, all of it faces the same endpoint. What that endpoint actually looks like is something physicists have spent serious time mapping out. And the picture they have drawn is unlike anything that happens in the universe today. When a star runs out of fuel, it does not simply disappear. It goes through a series of stages depending on its mass, eventually cooling into a dense, cold remnant called a white dwarf. Over billions of years, even white dwarfs cool further, becoming objects called black dwarfs. Dark, cold, inert, just enormous balls of carbon and oxygen atoms, packed tightly together, floating through a universe that has moved on without them. Current physics says black dwarfs would persist essentially forever. They have no energy source, no reactions to drive, no way to change. The standard model of particle physics, with its assumption of proton stability, predicts that these objects simply sit in the dark indefinitely. Long after all the stars have burned out, long after all the galaxies have drifted apart, black dwarfs would still be there. Proton decay changes this picture entirely. If protons eventually break apart, then every atom inside a black dwarf is carrying a timer. The carbon atoms, the oxygen atoms, every proton in every nucleus of every atom in that cold stellar remnant is ticking down. The process would be extraordinarily slow, but slow is not stopped over timeframes that make the current age of the universe look like a single heartbeat. The protons inside the black dwarf would begin to decay one by one. Each decay releases a tiny burst of energy. Each decaying atom transforms into something lighter. The solid structure of the star begins to change at the atomic level. As protons decay across the mass of the star, the material loses its atomic structure. The elements dissolve. What was once carbon or oxygen becomes a mix of lighter particles, positrons and photons and neutrinos, drifting away from the remnant into space. The star very slowly evaporates. Solid matter turning into radiation, gram by gram, proton by proton. Over timescales that require numbers with so many zeros that even scientific notation feels inadequate. Eventually, after a span of time so vast it cannot be connected to any human experience, the black dwarf would be gone, not collapsed, not exploded, simply dissolved. The atoms that once made up an entire dead star would be scattered as light and ghost particles across an expanding void. This would happen to every black dwarf in the universe, every planet that survives the death of its star, every asteroid, every moon, every solid body of any kind. The universe of the deep future would be a place with no solid objects at all. Cosmologists who study the very long-term future of the universe have mapped out a series of eras, each one stranger than the last. The era we live in now, where stars burn and galaxies spiral and planets hold oceans, is actually one of the earliest and most active chapters in the full story of the cosmos. In the far future, the stars go out first. The gas clouds that birth new stars slowly get used up. Over tens of trillions of years, star formation drops to zero. The last stars burn down to cold remnants. Galaxies become collections of dark objects drifting apart as the universe continues expanding. The era of starlight ends. Then black holes dominate. The massive black holes at the centers of galaxies outlast everything else. They slowly absorb whatever drifts close enough and grow incrementally larger. But even black holes are not permanent. Through a process called Hawking radiation, black holes very slowly lose mass by emitting particles at their edges. Over time frames that make stellar death look instant, even the largest black holes evaporate completely. The era of black holes ends. What remains, if protons are stable, is a collection of cold black dwarfs, lone electrons, photons, and the occasional lightweight particle drifting through a vast, cold, expanding emptiness. The universe becomes dark, cold, and essentially static. Matter persists in solid form, frozen and inert, for what might be an infinite duration. If protons decay, the ending is different. After the black holes evaporate, the remaining black dwarfs begin their own slow dissolution. Over timescales requiring a number with more than 30 zeros, each black dwarf radiates away its mass as the protons inside it decay. The solid matter evaporates. The final solid objects in the universe dissolve into light and ghost particles. Eventually, the universe contains no solid matter of any kind, no atoms, no molecules, no structure at any scale, just a thin, cold fog of photons, electrons and neutrinos, expanding outward through a geometry of space that continues to grow. A block of iron sitting alone in a field, given enough time, would undergo the same process. The iron would not rust, the iron would not melt. The atoms would one by one lose their protons, transform into lighter configurations, and eventually the block would simply cease to exist as matter. Its mass would have converted entirely into radiation. This is the universe that proton decay leads to, a final state of pure light and ghost particles spread so thin across such an enormous volume of space that the universe would be, for all practical purposes, empty. And the atoms in your hand right now are the same atoms that would one day be part of that fog. When a proton decays inside an atom, the atom does not quietly disappear, it breaks apart, and the electron that was orbiting the nucleus is suddenly homeless. Electrons are stable. Unlike neutrons, unlike hypothetically decaying protons, electrons appear to be genuinely permanent under every test ever conducted. The electron has no lighter charged partner to transform into. It has nowhere to go. So when a proton decays and the atom falls apart, the electron does not decay along with it. It detaches from the nucleus and drifts free. In the deep future universe where proton decay has dissolved all solid matter, the result is an expanding population of lone electrons with nothing to attach to. Every atom that has ever existed eventually releases its electrons when the protons at its center decay. The electrons do not annihilate each other easily because they all carry the same negative charge and repel one another. They drift apart, combined with the photons released by proton decay events and the neutrinos that carry away half the energy from the supersymmetric decay pathway. The universe in this scenario becomes a very cold, very spread out collection of three types of particles: photons carrying energy but traveling in all directions, neutrinos barely interacting with anything, and lone electrons drifting through an expanding space with no atoms left to join. This is one of the loneliest pictures in all of physics. Not loneliness in any emotional sense, just an accurate description of the physical state. The electrons cannot form atoms because there are no nuclei left. The photons carry less and less energy as the universe expands and their wavelengths stretch. The neutrinos do essentially nothing. The universe approaches a state physicists sometimes call heat death, where the temperature everywhere is essentially uniform and no energy gradients exist to drive any process. No chemistry, no nuclear reactions, no structure, just particles distributed as evenly as an expanding universe allows. The electron, the particle that makes chemistry possible, that carries electrical current, that bonds atoms into molecules and molecules into life. ends up as the final relic of a universe that once contained stars and planets and everything we have ever known. It sits in the dark, drifting, with no atom left to call home. The question of how the universe reaches this state, and whether proton decay is what triggers the final dissolution of matter, connects to a much older and deeper mystery, one that reaches back to the very first moments of the universe. The Big Bang produced matter and antimatter in nearly equal amounts. Every particle created in those first moments had a corresponding antiparticle with the opposite charge. When a particle meets its antiparticle, both annihilate, converting entirely into pure energy. If the universe had produced exactly equal amounts of both, every particle would have found its partner, and the entire contents of the cosmos would have destroyed itself in a flash of radiation. We exist because that did not happen. Somewhere in the early universe, matter won, by a tiny margin. For every billion antiparticles produced, roughly 1 billion and 1 matter particles appeared. The billion pairs annihilated. The 1 extra matter particle per billion survived. Every proton, every electron, every atom in the observable universe descended from that tiny surplus. The question of why matter slightly outnumbered antimatter is one of the deepest unsolved problems in physics. Without an answer, scientists cannot explain why anything solid exists at all. The field studying this question is called baryogenesis, meaning the origin of the matter surplus. Grand unified theories offer a potential answer. For matter to have won over antimatter in the early universe, certain conditions had to hold. One of them is that protons and their components could not be perfectly conserved. The number of protons in the universe had to be able to change. Processes that created or destroyed protons had to be possible. This is the same requirement that leads to proton decay. If proton number can change, then in the early universe it changed in a direction that favored matter over antimatter. And if it can change in one direction, it can also change in the opposite direction. A proton can spontaneously transform and reduce the total matter count of the universe. The connection runs deep. The very process that allowed matter to exist at all, the violation of perfect proton conservation in the early universe, is the same class of process that predicts proton decay today. The two phenomena are linked by the same underlying physics. Finding proton decay would not just confirm a detail about particle physics, it would also shed light on why the universe is made of something rather than nothing. The matter surplus that allowed stars, planets, and life to form was a direct result of the same laws that might be slowly dissolving matter now, one proton at a time. At a fundamental level, the universe owes its existence to an asymmetry, a slight tipping of the scales towards matter over antimatter in the first fraction of a second after the Big Bang. Remove that asymmetry, and the universe is a featureless expanse of radiation, perfectly uniform, carrying no structure of any kind. We can measure it indirectly by counting the photons left over from matter-antimatter annihilation events. For every proton in the universe today, there are roughly 2 billion leftover photons from those ancient annihilation events. The ratio tells you how lopsided the original surplus was. Tiny, but decisive. Physics has a name for the conditions required to generate this asymmetry. Andrei Sakharov, a Soviet physicist, identified 3 requirements in 1967. One of them is that the laws of physics must allow for processes that change the total number of matter particles. Proton decay is exactly that kind of process. If the laws of physics strictly conserved proton number at all times, no such asymmetry could ever have developed. The universe would have been locked in perfect balance. Matter and antimatter would have annihilated completely. Nothing solid would remain. The fact that we exist is indirect evidence that proton conservation is approximate, not absolute. Something in the early universe violated that conservation rule, at least briefly, at least partially. Grand unified theories were designed in part to explain how that violation happened, and those same theories predict that the violation is still happening today, at an incredibly slow rate. Protons are not perfectly stable now. They were not perfectly conserved then. The story of baryogenesis and the story of proton decay are chapters of the same book. Finding a decaying proton in a tank of ultra-pure water in Japan would therefore accomplish something far beyond confirming a detail in a physics model. It would close a loop that runs from the first instant of creation to the present. It would show that the laws responsible for making the universe real, for generating the surplus of matter that led to everything, are still quietly operating in the atoms around us. The hunt in Japan is not just about particle physics. It is about tracing the reason existence happened at all. Stand at the base of a mountain range, the Rockies, the Himalayas, the Appalachians. Some of these rocks formed hundreds of millions of years ago. The atoms inside them are old. Some of the hydrogen atoms in those rocks trace their history back to the first few minutes after the Big Bang, formed before the first stars ever ignited. Those atoms have been sitting in solid form for an enormous stretch of time, and if proton decay is real, every proton in every atom of every rock in every mountain range on Earth is sitting on a clock. The clock ticks at an almost impossibly slow rate. The odds of any individual proton decaying in the next million years are remote. In the next billion years, still remote. But the clock does not stop. There is something strange about this idea when applied to objects we think of as permanent. Mountains feel eternal. Solid rock feels like the opposite of transience. But the most durable objects in everyday experience, stone, metal, ancient crystal formations, are built from the same particles, subject to the same theoretical instability as everything else. The rocks on the ocean floor, the iron core of the Earth, the carbon in ancient fossils, the calcium in your bones, every piece of matter we interact with, every material humans have ever used to build anything, exists inside the framework of a universe where the fundamental building blocks might have a lifespan. This does not mean matter is fragile. On human timescales, on geological timescales, protons behave as though they are permanent. The mountains will stand. The iron will not spontaneously dissolve. The decay rate is so slow that for any practical purpose, matter is as stable as it has ever seemed. But practical permanence and absolute permanence are different things. Chemistry assumes protons are stable. Biology assumes protons are stable. Engineering assumes protons are stable. All of those assumptions are correct for every situation those fields will ever face. The decay, if real, operates on a time scale that makes geological time look like a morning commute. The philosophical weight of the idea is what lingers. The universe might be a place where even the most solid things are temporary at the deepest level, where permanence is an illusion created by the gap between a human lifespan and the timescale of physics. The rocks feel ancient to us. To the universe's actual clock, they are barely formed. And the experiment listening for this in a mountain in Japan is trying to confirm whether this gap between feeling permanent and being permanent is real. The Super Kamiokande sensors have recorded hundreds of millions of events. Every one of them, after analysis, resolved into a known background, a cosmic muon, a neutrino interaction, a trace of radioactivity. The ledger of candidate events has been reviewed carefully, and every entry has been explained by something other than proton decay. Imagine the moment when that changes. A cluster of sensors fires in a specific pattern. The analysis software flags it as a candidate. The energy adds up correctly. The geometry of the light rings matches the expected signature. The event originated from inside the fiducial volume, deep within the water, from nowhere and from nothing external. The background explanations are checked one by one, and none of them fit. The team reviews it again and again. They run it against every known source of noise. They check the sensor timing for calibration errors. They look for hardware faults. Everything comes back clean. The event stands. A confirmed proton decay event would be the most significant result in experimental physics since the detection of gravitational waves in 2015. And arguably more significant than that. It would be the first direct evidence that matter itself is fundamentally unstable. It would confirm that the forces of nature are unified at high energy, that grand unified theories are on the right track. It would provide the first experimental window into physics at energy scales far beyond what any particle accelerator on Earth can reach. It would also immediately point towards the antimatter mystery. If protons can decay, the mechanism that caused the matter surplus after the Big Bang becomes experimentally accessible for the first time. The confirmation would open a new era of theoretical work, aimed at connecting proton decay rates to the specific asymmetry between matter and antimatter that allowed the universe to exist. Every major physics institution in the world would shift focus. Theorists would race to determine which specific grand unified theory the decay pattern matched. Experimentalists would start designing detectors to measure the decay rate more precisely. Funding for larger detectors would become far easier to justify. One event, one blue flash in 50,000 tons of dark water, would redirect the entire field. The scientists watching the tank know this. They have known it for decades. They continue watching anyway in a mountain in Japan, in the dark, with extraordinary patience. There is a version of this story that sounds almost absurd when you describe it plainly. Hundreds of physicists and engineers spent years designing and building a tank the size of a 12-story building. They buried it inside a mountain in Japan. They filled it with the purest water on Earth. They lined it with 11,000 glass spheres, each one capable of detecting a single particle of light. They turned out the lights, and they started waiting. They are waiting for a single blue flash, one event, somewhere in 50,000 tons of dark water, that would confirm a proton finally died. The experiment has been running for nearly 3 decades. The flash has not come, and the team keeps watching. This kind of science sits at an unusual intersection. The practical and the philosophical overlap in a way that rarely happens in everyday research. The experiment is rigorous, methodical, and deeply grounded in mathematics. Every aspect of it follows the scientific method precisely, but the question it is asking reaches beyond the technical. It is asking whether matter is real in a permanent sense, or whether everything solid is a temporary arrangement of unstable particles waiting for a timer to expire. Humans built the pyramids partly because solidity feels like permanence. We build in stone and steel because we want to create things that last. Every culture has some version of the desire to make something that endures. The proton decay experiment is, among other things, a scientific investigation of whether endurance is actually possible. If protons decay, nothing endures. Every atom ever placed in a wall, a foundation, a monument, a vault, is sitting on the same ticking clock. The pyramids are as temporary as a sandcastle, just on a timescale that makes the difference invisible. If protons are stable, the universe in its deep future is a cold, dark, static place, where the last black dwarfs float forever through expanding space, never dissolving, never changing, outlasting time itself in a way. Both outcomes are scientifically interesting. Both have philosophical weight. The team in Japan is not trying to prove one philosophy over another. They are trying to find out which universe we actually live in. That search, conducted in silence, in a mountain around a tank of extraordinarily clean water, is one of the most quietly ambitious things the human species has ever attempted. After nearly 3 decades of silence from the world's most sensitive proton decay detector, a question has earned its place in the conversation. What if protons genuinely never decay? Physics has no confirmed law that requires proton decay. The grand unified theories that predict it are compelling and mathematically elegant. But elegance is not evidence. Every version of these theories that has made a specific testable prediction has been eliminated by the experiments. The surviving theories survive precisely because their predictions remain just out of reach of current instruments. If protons are truly stable, it means conservation of baryon number is an exact law of nature, not an approximation. It means the forces of nature do not fully unify at high energies in the way grand unified theories predict. It means the mathematical symmetry that connects quarks and leptons, which seemed so beautiful on paper, does not actually exist in nature at any energy scale. For theoretical physics, this would be a serious problem. The standard model of particle physics, which describes all known particles and forces with extraordinary precision, does not explain several things that physicists consider glaring gaps. It does not explain why matter outnumbered antimatter after the Big Bang. It does not explain the origin of the forces it describes. It does not explain dark matter or dark energy. Grand unified theories were built partly to address some of these gaps. If proton decay is ruled out, the primary experimental test of grand unified theories disappears. Physicists would need a different way to probe the high-energy unification of forces, and at the moment, no alternative with comparable experimental reach exists. The universe in a proton-stable scenario also looks different in the deep future. Without proton decay, the black dwarfs that form after stars die persist indefinitely. The atoms in them are locked in permanent solid form. The universe becomes a dark, cold place filled with these dark, frozen objects, spread further and further apart by the expansion of space, unchanged and unchangeable, drifting through an infinite dark. There is something both peaceful and disquieting about that picture. Matter wins. Everything solid persists. The universe grows colder and emptier, but never fully dissolves. Whether that future is comforting or not depends on your perspective, but the experiment running in Japan is not influenced by perspectives. It measures what it measures, and right now, it measures silence. At the outer edge of theoretical physics, a small number of researchers have been exploring a stranger possibility. What if the stability of a proton is real here, real now, but would not be real everywhere, or at every moment in the history of the universe? Standard physics treats the laws of nature as universal. The same rules apply everywhere in the cosmos at all times. A proton in a galaxy 10 billion light-years away obeys the same physics as a proton in a lab in Tokyo. This assumption of universality is deeply embedded in how physics works and has been confirmed in every observation ever made. But the assumption rests on something that took time to appreciate. The vacuum of space has physical properties. It is not simply empty. It carries an energy density that influences how particles interact. In the very early universe, the vacuum was in a different state than it is today. The transition from that early state to the current one is called a phase transition, and it happened as the universe cooled after the Big Bang. During that phase transition, the rules of particle behavior were different. Forces that are separate today were unified. Symmetries that are broken today were intact. Protons, if they existed in that early phase, would have behaved according to a different effective rulebook. Some theoretical models extend this idea in an uncomfortable direction. They suggest the vacuum might not be in its absolute lowest energy state right now. The current state might be metastable, like a ball resting in a valley that is not the deepest valley on the landscape. If that is true, the vacuum could eventually transition to a lower energy state, and that transition would change the laws of physics throughout the universe. In a metastable vacuum scenario, proton stability could shift. Under current conditions, protons are stable. Under the new conditions following a vacuum transition, they might decay rapidly. The transition would propagate outward from its origin point at the speed of light, changing the rules of physics as it expanded. This scenario is entirely speculative and sits well outside the mainstream. The experimental consequences would be dramatic and untestable in advance. But it shows how deep the question of proton stability reaches. It connects the behavior of a single subatomic particle to the fundamental structure of space itself. And it raises the possibility that the silence from the detector in Japan is not telling us that protons live forever. It might be telling us that protons are stable under conditions that define the current universe, and that the real test of their permanence lies in environments we have no way to probe. The experiment can only hear what happens in the world it was built for. What happens beyond that is still beyond reach. The water in the Super Chemiocande tank sits in the dark right now. The sensors are active. The electronics are reading out. The software is processing signals continuously, sorting noise from candidates, flagging events for review, building a data record that physicists will study for years. The protons in that water have been watched for nearly 30 years. They have given up no confirmed secrets. The lower bound on their lifespan has climbed so high that only the most exotic and difficult to test theories remain alive. The simplest explanations are gone. What is left is a field navigating a question it cannot fully answer yet. This is where physics actually lives. The resolved questions, the ones with clean answers backed by solid experiments, fill the textbooks. The unresolved ones live in underground tanks, in theoretical arguments that span careers, in papers presenting bounds rather than discoveries. Proton decay has been one of the largest unresolved questions in particle physics for 50 years. The next chapter in the search belongs to Hyper-Chemiocande. When it reaches full operation, it will watch more than 5 times as many protons simultaneously. The lower bound will rise faster. If the true proton lifespan falls within the range the new detector can probe, a signal might appear within the next 2 decades. If it does, the confirmation will arrive quietly, a cluster of sensors firing in a specific pattern, software flagging a candidate, physicists running checks, a result that does not announce itself but requires careful work to establish. If no signal appears even after Hyper-Chemiocande has run for a decade or 2, the pressure on grand unified theories will become severe. The surviving models will be pushed into corners of parameter space that are theoretically awkward and hard to justify. The field will face a genuine reckoning, and still, even then, the absence of a signal would prove nothing absolutely. A long enough proton lifespan always leaves room for the decay to be happening just below the current detection threshold. The question can be squeezed but never fully closed by a null result. Science works this way at the frontier. Questions narrow, evidence accumulates. Theories rise and fall. The answer approaches, but the final step often requires a generation, or several, somewhere in the dark water of that tank. Right now, an enormous number of protons are sitting in silence. Each one has been stable for longer than the Earth has existed. Each one is, theoretically, moments away from transformation, in the sense that any moment across a vast timescale can be called a moment. Whether any of them will break, and whether we will ever see it happen, remains the question. The sensors are watching.